Okay, welcome everyone. Today we're very happy to have Herman Verlinde from Princeton, and he's going to tell us about a string dual of SYK. Please take it away, Herman.
Okay, I have to click continue. Okay, well, it's good to sort of, even if it's virtual, to visit Chicago. I'm hope of course that next time we can do it in person. So indeed, what I'll be talking about today is a proposal that we put out in a paper together with graduate student Akash Gul a bit more than a month ago. And I gave one or two talks about this before, but more in the form of a discussion. So the slides are kind of informal. And indeed, I would like to encourage people to indeed interrupt at any time that you have a question. Because part of the reason for giving this talk was also to get input and feedback sort of on this idea. So to motivate, I don't think it needs necessarily that much motivation to sort of why we're looking at this particular question, but still it's good to give it a little bit of context, is that clearly, again, in string theory, our goal is to describe quantum gravity. We've have ways of making systems in string theory, model systems in string theory that we believe describe black holes in a quantum setting. And we've learned a number of things about it, but still, even within ADS-CFT, it has been hard to find models, non-trivial dynamical systems that capture aspects of the black hole dual systems in a soluble way where both sides of the duality can be sort of analyzed sort of explicitly. And this is sort of one of the achievements that the SYK model brought in, is that it captured certain aspects of low dimensional black holes, and in particular, or more generally, black hole dynamics. And in particular, it captured this feature that the quantum many-body dynamics would have to be maximally chaotic in a way that reflects the interactions of particles near a black hole horizon. And so I'll write down, at least I'll remind you of what the SYK model looks like. And again, it's a non-trivial interacting system. It's a 0 plus 1 dimensional quantum mechanical system. And therefore, it's sort of a model of a holographic description of a two-dimensional black hole. And it has a number of those features. But of course, part of the motivation of our paper is really that if this is true, that this SYK quantum system potentially has this dual gravity interpretation, how are we supposed to think about this from the point of view of string theory? I'm kind of partly, I would say, a believer that quantum gravity systems are pretty rare. Maybe they capture gravity, indeed captures certain universal features of quantum many-body systems, but still, quantum gravity is a delicate structure, and string theory has up to now been able to incorporate all the successful models of quantum gravity. So the question is, does it incorporate the SYK model? So it's natural to look for that. So in SYK, you start with a large number of Majorana oscillators that satisfy this anti-commutation relation up here. And the main feature of it is that it's sort of, in some ways, a maximal scrambler, meaning that it has this many-body interaction. P is an arbitrary number in the following, and these are these random couplings that are sampled from a Gaussian distribution. And this is basically, that's the SYK model, and indeed exhibits this features of maximal chaos, and it has a low energy sector that indeed that is similar to a two-dimensional model of gravity known as JT gravity. One aspect of the SYK model, as I already mentioned, is that the couplings are random, and indeed the way of sort of solving or analytically treating the theory, what's often done then is to introduce then this disorder averaging, where one explicitly integrates out, or at least integrates over the distribution of random couplings. So let me already write down that particular Lagrangian, or at least what you get after integrating out the couplings. You get a bilocal quantum mechanical system, again, where now there's a double integral over time because of the disorder averaging. And this interaction is this 2-point function to the power p, where j squared is, again, this sort of average size of the coupling. Again, this is a nonlinear fermionic interaction. And if one would be looking for a string dual, one could either imagine finding something that looks like this within string theory, or one could try to look for something that looks more like the non-averaged theory, like we have over here. And this non-averaged theory it would come with a large number of random numbers. What I'll be doing in the following, I'll be looking at a more sort of restricted class of theories in string theory, which is minimal string theory. And it should not come as a surprise, therefore, that indeed, if we're going to find a connection, that we're going to find the connection actually with this disorder averaged theory. But it's part of a more general discussion whether indeed looking at lower dimensional holography, or maybe holography in general, whether this feature of having to average over couplings or average over systems is something that is sort of a necessary feature of holography or not. So that will naturally come back in this discussion as well. So anyway, that's sort of the introduction. Again, this is the SYK model, and how do we find it in string theory? I'm not sure if there are questions at this point. I can sort of then just move to the next part of the discussion. So I'll essentially be following sort of our paper. So let me just introduce the next player in the game. So it's been known already that, as I mentioned, there was JT gravity, which is just two-dimensional gravity restricted to the space of constant curvature metrics. And that had been already recognized as to be a limit, essentially, of minimal string theory. And therefore, it might not be unnatural to be looking also for a potential connection between minimal string theory and the SYK model. So let me just, schematically give you a quick introduction into minimal string theory. So minimal string theory, you take a minimal model conformal field theory, which is C less than 1, the central charge less than 1 theory. It's often parameterized indeed in terms of a parameterization that's similar to Liouville theory. And indeed, the minimum CFT by itself would have to be coupled to a Liouville sector in order to have a total central charge equal to 26. And the way the central charges are then labeled is by means of two integers that are labeling the minimal model, little p and little q. And those integers, again, would have to be special in order to have a unitary theory. But in the following, I'll be sort of just talking more generally about p comma q minimal strings. Actually, later on, we'll take q to be equal to 1. But as most people who studied the CFT literature, minimum models indeed have a finite set of operators that are labeled also by two integers, which I'll denote by R and S. And R and S run from 1 to p minus 1 and 1 to q minus 1. And you can think about the operators in the theory essentially as spanning a discrete lattice like this. So you have operators for every value of the two integers. In analyzing sort of the spectrum or the interactions of the theory, it's useful indeed to look at these primary fields and look at their gravitational dressed cousins, which indeed are going to be the vertex operators of the string theory. And those vertex operators span something that's called the ground ring, So there's an algebraic structure that one can identify. In the following, and this is sort of a part of the paradigm of open-closed string duality, as we're going to be introducing the D-branes in this theory. And indeed, the idea is going to be that the SYK variables, which are the fermions, are going to be open strings in this particular theory. And they're going to be open strings that are going to be stretching between two types of branes in this theory. So they're basically the open strings that live on brane intersections. And it's sort of known in string theory in higher dimensions as well, that precisely on brane intersections, you're going to typically get fermionic strings. The strings that stretch between the two are often fermionic. And this will happen here as well. So the two types of branes in minimal string theory, again, are the FZZT branes and the ZZ branes. The ZZ branes are like deep particles. They're localized, or the instantons perhaps even. So they're localized in the Liouville direction. And the FZZT branes are extended in the Liouville direction. So you can think about them as Neumann boundary conditions for the Liouville field. And on the boundary, you can add a parameter, which is the boundary cosmological constant. And it turns out that indeed that boundary cosmological constant you can think about as being kind of the parameter that governs the conformal dimension of the field that will go in the open string channel. So typically what you could do is you could have a ZZ boundary condition on one side. You could have an FZZT boundary condition on the other side with a parameter mu sub b. And then there's a field going in that channel labeled by a conformal dimension, which is the Liouville, which you can parameterize by the Liouville momentum. And then the relation between the cosmological constant, boundary cosmological constant, and the Liouville momentum is given by this formula. Finally, and again, this is something that Emil discovered in that there's a relationship actually between these two types of branes, the FZZT branes and the ZZ boundary states have a particular relation. The ZZ branes indeed are going to be labeled by integers. And it turns out that there are special Liouville momenta given by an integer over b and an integer times b. If you take that particular lattice of momenta, you're labeling the ZZ branes. But they are actually given by the difference of two FZZT boundary states. So this is the lightning review of minimal string theory. Just the summary is that it's minimal models coupled to Liouville, and there are two types of branes in the story. Now, of course, we want to go towards holography, and in holography, basically, one of the sort of the themes that you do within string theory, whenever you have a D brane in string theory, it's always going to be useful to look at the limit where you have a very, very large number of a particular type of D brane. And then you look at the field theory or the quantum mechanics associated with that large number of D branes. In this case, we have two types of D branes. We have the ZZ branes and we have the FZZT branes. And you can take one of them to be the large number of branes. If you take a large number of ZZ branes, you're going to get open strings that reconnect between the ZZ branes. And those open strings will make up a matrix integral, basically, because we don't really have time in this story yet. And therefore, the open strings that stretch between the ZZ branes will have some dynamics. And one of the lessons in the early 2000s is that the matrix models that people had been writing down in the early 90s for minimal string theory could be interpreted basically as the open string dynamics on a large number of ZZ branes. So the two, now in the case of the PQ minimum models, it turns out that one can capture the PQ minimum models by means of a two matrix model. So that's the next player in the game. So unless there are questions about the minimal strings, I'm going to talk about the two matrix model. So the basic...
a naive question, please. There's no interpretation of the random couplings J in the SYK model yet in the string theory picture.
Yeah, that's too early. I'll come back to that later. Oh. I indeed introduced the question, but I'm not going to answer it yet. So currently, again, we're going to be looking indeed at the ZZ strings, so open strings, which are the variables in the matrix integral. Later, we'll be talking indeed about the ZZ FZZT strings, which are going to be the SYK variables. So so there's a paper by Dow, Kazakov, and Kostov in the mid-90s, following on earlier papers indeed by, among others, Michael Douglas, who so in the early 90s, people could capture all the non-perturbative, at least the summation over all the higher loop contributions of open string, of minimal string theory by means of a double-scaled matrix integrals. And in order to have matter on the string worldsheet, one needs at least two matrices. And it turns out that for the PQ minimum models, indeed, it's enough to have two matrices. There are also other formulations of PQ minimal string theory where you make use of more than two matrices, but here in this case, there are going to be two matrices, A and B. And each of them will have their own potential, V of A and V of B, W of B. And roughly speaking, the order, at least, yeah, it's correct that the order of the interaction, so these are both polynomials, and the rank of the polynomial will determine what kind of minimum model we're going to be looking at. So we have this matrix integral, and you still have to do a double scaling limit where you send n to infinity, and you tune the potential to a multi-critical point. And then the Feynman diagrams proliferate, and in that double scaling limit, you get the PQ minimal string. One way of understanding why two matrices is enough in this case is that effectively, when you have a matrix model, you can introduce something that's called then a spectral curve. And one way of thinking about the spectral curve is as follows, is that you indeed can introduce a probe in the system that you can either think of as essentially introducing a probe eigenvalue, so fixing one of the eigenvalues of one of the matrices, or essentially equivalently, you can introduce this operator psi of x, which is the determinant of x times the unit matrix minus the matrix over which you're integrating. So this determinant operator is actually thought of as introducing a D-brane in the story. Or you can think about it as essentially introducing a probe eigenvalue at the location x. The fact that this psi of x introduces a D-brane can be understood from the point of view of the Hooft 1/n expansion. If you draw the Feynman diagrams of the matrix model, the insertion of this operator, the determinant operator, introduces a boundary effectively to your Feynman diagrams, and that boundary will correspond to some location in the target space on which the open strings can end. And that location is parameterized by x, and this x is going to be the boundary cosmological constant of the corresponding FZZT brane. Now, one thing you can do is you can actually try to study the moduli space of this FZZT brane, and that moduli space in this case turns out to be something that's called, again, the spectral curve. And since there are two matrices in the story, there are going to be two coordinates of this spectral curve. One of them I can call x, and the other one I can call y. And it turns out that if you indeed go to the appropriate potential that describes the PQ minimum model, then the equations that specify the spectral curve will match with the equations that this ground ring that you derive from the CFT. So if you think about, so now I'm going back to this set of operators, you have two generating operators in this ground ring. One you can call X, and the other one we can call Y. They basically go in the two directions of this grid, and they satisfy some polynomial relation which matches with that of the matrix model. So that's one way in which one can make a link between the matrix model and the string theory. Is there a question at this point or comment?
Yeah, so there are presumably then two of these fermion operators where you have determinant of x minus a or determinant of x minus b.
Yeah, so I would call it y minus a or x minus b. Yeah.
Okay, okay, and so those are presumably constrained by these relations between the matrices A and B in some way.
Right.
So the spectral curve will presumably relate those in some way.
Right. So it's not. I wouldn't be so easy for me to write down because in the end, in the double scale theory, for example, the x and the y variable in some ways become canonical conjugate. It turns out that basically the curve becomes a quantum curve once you sort of go to the double scaling limit. But if you take the large n limit, you can sort of more classically introduce both branes, and then the relation would indeed be exactly that of the spectral curve. In the story that I'll be talking about, I'm only going to be talking about the FZZT branes that have this B matrix sort of sitting in there. So it's one of the types of FZZT branes. By the way, indeed, from the point of view of this grid, you can kind of think about the horizontal and the vertical directions indeed as locations. So I guess the branes that I will be introducing are the ones that sort of are more like horizontal here, whereas the other branes that you would introduce would go like vertical, like that.
Right. And I should think of this as some kind of phase space.
That's correct. You can think about it as a phase space. And what I'm going to do is I'm going to actually introduce an array of branes. So basically, I'm going to do this. Although actually I should interchange x and y because I'm going to have many x values. So I'm going to introduce an array of branes among locations that are the eigenvalues of some matrix that I'll call x sub q. So I'm going to introduce this object.
Okay.
Now immediately, of course, this was known. This was all known in the literature, and indeed, the beautiful papers indeed by Seiberg and Shi that make this link between the matrix models and the minimal strings. And there's also a paper indeed by Kazakov and Kostov that sort of look at it from the matrix perspective. Now, a natural thing you can do once you introduce indeed a determinant operator is indeed to represent the determinant by a Grassmann integral. So indeed one introduces a psi dagger and a psi, and this operator, this determinant operator that I have up here, psi of xq, I can also write it like this. As I mentioned, the A and the B matrices are the strings that stretch between two ZZ branes. This psi of x corresponds to introducing an FZZT brane, on which the open strings can end. So already at this moment, which is just a trivial algebraic step, but at least we're learning something about string theory, that these psis, indeed, they have an index I, which runs from 1 to n, which is the A and B matrices are n by n matrices. They also have an index A, which goes from 1 to big Q, where big Q is the rank of that matrix X sub Q. It's the number of FZZT branes that I'm introducing. So it's pretty obvious that if we give these psis an open string interpretation, that they should be thought of as a string that stretches between the ZZ brane and the FZZT brane. And later on, it will be helpful to introduce just an arbitrary nomenclature, I guess, where the n index, the I index is called the color index, and the A is called the flavor index. Indeed, there's a paper, I think, of David Kutuzov and Nati and two other authors, I think David Shi, where they indeed look at the strings that stretch between the ZZ branes and the FZZT branes, and they indeed verify through the analysis amplitude that that these are fermionic, have fermionic ground states. So that interpretation is indeed confirmed from a string theory perspective. Now, so up to now, again, this is all relatively standard. And now I'm going to make one other step, which is in fact also standard, but perhaps a little bit less well known. What I'm going to do is I'm going to go to a special minimal string theory where I'm basically going to drop the potential W of B, but I'll be reintroducing it by inserting one of these operators psi. So if you wish, we're going to use psi as a means of parameterizing the potential W of B. So and one way of thinking about this physically is what we're going to do is when we drop the potential W of B, we're basically putting Q equals 1, because then the W becomes a linear potential, and I can absorb that in a shift of A if I want. So basically, by dropping W of B, we're introducing something that you could call the P,1 minimal string. And the P,1 minimal string is actually, let me back up a little bit. The 2,1 minimal string turns out to be topological gravity. That's the topological string theory. And that topological string theory computes the intersection numbers of the moduli space of Riemann surfaces. That's the 2,1 string. The 2,3 string is where P is 2 and Q is 3. Is pure gravity. That's just pure Liouville gravity. The 4,3 string would be Liouville gravity coupled to the Ising model. But if I take the P,1 string, it turns out that that's topological gravity coupled to a topological minimal model. So there's still going to be matter, but the fact that Q is 1 means that the string theory will actually be topological. And then I'm going to reintroduce couplings in this theory by means of this determinant operator. And the famous papers work by Kontsevich in the early 90s, where he actually was able to explicitly solve these topological theories. And he actually wrote down a matrix model that solved topological gravity. And the Kontsevich matrix model is actually the matrix model that I'm about to derive. And that matrix model is the matrix model that lives on the FZZT branes. So the next step is actually the step that Kontsevich took, but I'm slightly generalizing it because Kontsevich, at least his most famous work, is for P equals 2, but I'll be doing it for arbitrary P. So I'm making this particular replacement that I have over here, that I replace the potential by that determinant. And you can always do this, at least if this determinant is, if the matrix X is big enough, you can, for any potential, you can always make this replacement. In some of the literature, this is called the Kontsevich Meeba transform, because these things are tau functions where Meeba did his work. But indeed, Kontsevich basically says that if you have a potential and it has coupling constants T sub k in the Taylor expansion of W, then those Taylor expansion modes are basically obtained by Taylor expanding the right-hand side through this dictionary. And this is indeed how Kontsevich relates his couplings to the couplings of the original matrix model. So now I'm basically at the starting point of our proposal, which is this particular partition function up here, which is taking Q FZZT branes in the P,1 minimal string, but from the matrix model perspective. Are there any questions about this particular starting point? Because it turns out that this expression here is in fact a version of the SYK model, which I'm going to show in the next 1.5 slide. But the claim is that if I take this particular expression and I would take a double scaling limit, which means I take n to infinity, so this traces over an n by n matrix. if I take n to infinity in this matrix model and I do some appropriate tuning, then this would describe indeed Q FZZT branes in P,1 minimal string theory. The locations of those branes on the spectral curve are parameterized by this matrix XQ. This XQ is not dynamical. It's not integrated over, we're integrating over A and B. Let me make one comment. XQ is a Q by Q matrix. This identity matrix is an N by N matrix. This identity matrix is a Q by Q matrix, and this is the N by N matrix. That's diagonal. Sorry, that's dynamical. These two matrices commute. For people that have studied the SYK model, this may already look a little bit SYK-like, because in the SYK model, indeed, what I can do, I can rewrite this thing indeed as a fermionic integral. I've done that down here. So this is equivalent to what I have up here. This already looks very much like something that people that have studied SYK might recognize. The only difference with SYK is that indeed there are going to be, in that case, Majorana fermions. In that case, often one introduces something that's called the self-energy, which a field that's called sigma, a field that's called sigma, that basically sits at this location, and then this x would be the time derivative. So basically, the step is going to be to go from this particular expression to something where this will be similar to a time derivative. The only point is that this xq commutes with B, or at least this matrix combined matrix commutes with B, but we have to do a transformation, which we'll see in a second, that will flip the color and the flavor indices. Anyway, so here we go. At this point, it becomes easy because now B is linear. And I'm going to sort of rewrite this thing further by integrating out B.
In that analogy, the sigma variable also depends on time.
Correct.
So it's not quite the same because in this case, the analog of the time derivative and the sigma don't commute. Do commute rather than in the other case where they don't commute.
Right, precisely. So I'm going to fix that problem.
Okay.
And indeed, because partly I'm going to do the same thing as what Mom would do with the sigma matrix, because you can integrate out the sigma matrix, but in this case, I'm going to integrate out the B matrix. And that I'm going to get a delta function that will equate this A with the bilinear of the fermions. I didn't write down, oh, I forgot, I have to restart my, it's coming back. Yeah, I have to make sure that I sometimes engage my laptop, my iPad. But anyway, so if I integrate out B, I get this delta function, which will allow me to solve for A. So this V, this potential will become a potential of the bilinear of the fermions. And the kinetic term is then just still psi dagger X tensor 1 times psi. Are there questions from here to here? I think that's probably should be clear. Now comes sort of the next trick is the following, is that I'm going to use something that's called in the literature, in the random matrix literature, the color flavor map or the color flavor transformation. Because basically, indeed, the psi dagger psi that I have over here, up here, is this particular combination where indeed I sum over the A in the flavor index, but I have a matrix in the color space. That's what this psi dagger psi is. But if I have a trace expression like this over an n by n matrix, but each n by n matrix looks like that, I can just cyclically permute this psi dagger to the other side and write it like that. And now it's a trace over a Q by Q matrix of a like that. So this is a trivial rewriting of the same trace, but now indeed I've rewritten it as a Q by Q matrix. And give me a second. I realized. So now what I can now do, just write it explicitly and still as a matrix, as an integral over fermionic variables. So basically, the thing that I had up here, this expression up here, this one here, I can rewrite it as this expression down here, where this GAB is now a Q by Q matrix. So are there any questions about this? Because this is basically my matrix SYK model. So the thing that at least is encouraging is that indeed we're going to get this higher order fermionic interaction, which is basically this SYK type interaction is sitting here. But you can see already that this is actually the SYK model after this order averaging. So it's now bilocal in flavor space. So there's this A index and there's the B index. So it's bilocal in flavor space. It has an interaction. Sorry, it has a kinetic term. But in the kinetic term, this thing would have to become the time derivative. Notice also that this matrix XQ indeed no longer commutes with this GQ matrix. And one thing I could do is I could actually introduce a sigma AB matrix that will basically implement this identity here through a delta function. So I can write it completely as the SYK model, except that I don't have time. I have this flavor index A and B.
Quick question.
Yeah.
To just have this power, the G to the P, it's sufficient to take the Q goes to infinity limit first, or do you need to take the N goes to infinity limit first here?
Yeah, it's a good question. So let me make one comment. So in the matrix model that one typically writes down for getting the minimal string, you have this potential V of A, and V of A is a pth order polynomial. And it's not obvious that it's okay to only keep the pth order term. Although it's still true that typically one tunes towards the pth order critical point. But it's not entirely obvious that that's the same as having just the pth order term. One thing is true, however, is that if I write down this potential as a function of psi dagger psi, I can do this color flavor map. Then it's a potential of psi dagger. And then once I know that psi dagger is actually a sum over n terms, if I rewrite that function of psi dagger in terms of this variable GAB has a factor of 1 over n in front of it. So if I look at the n scaling of the different terms in the potential, it's the highest order term that has the highest power of n. So the fact that the potential is just the highest order term is something that kind of follows from large n scaling. So I certainly want to take n large. But as you already said, in the end, I want to also take a continuum limit, and the continuum limit will only arise if Q becomes large. And it turns out that in order to really get a continuum limit, you definitely want to take Q even bigger than n. So in the end, there's still some subtleties of how to actually go from this particular matrix model to the continuum theory. Let me make another few comments. So in order to really, again, make the connection with minimal string theory, one has to take a double scaling limit, which I haven't taken at this point. At this point, I took n and q to be just very large, but I didn't yet take the scaling limit. But to some extent, the argumentation that I'm using here, I think is okay. And a lot of the times, we identify the low energy degrees of freedom of string theory by first truncating the string spectrum. So indeed, if I have n ZZ branes and Q FZZT branes, The low energy open string theory, I would claim, would have to look like this, plus additional modes. And then afterwards, you can start trying to take the appropriate scaling limit so that you actually recover the full string theory. But as you anticipate, indeed, we're going to be taking a large Q limit pretty soon, because in the end, we want to get the continuum SYK model. Are there further questions at this point?
Yeah, I had a question. So your kinetic term XQ can be any matrix.
Yeah, in principle, yes. Later on, I'll indicate actually that the matrix. Of course, we're going to pick one that will give us the time derivative. There might be motivations to pick another one. It turns out that the matrix that gives the time derivatives will still have a pretty natural interpretation from the point of view of minimal string theory.
Mm-hmm.
But indeed, the XQ is in principle a parameter that one can choose, a set of values that one can choose. Now, let me make one other comment, and this is actually sort of also a subtle point. In the SYK model, this interaction term will actually look like a double integral over, say, 2 time variables of just the pth power of a bilocal function. Whereas here it looks like the trace of a matrix to the power p. That doesn't quite look like the pth power of a bilocal function. So the question is, how do I go from matrices to functions of 2 variables? Now, it turns out there's a relatively natural way of doing that by introducing something that are called clock and shift matrices, or for those people who in the past have studied the non-commutative torus, may actually recognize sort of the following sort of parameterization of matrices. So what you do is you introduce they're down here at the bottom. So this is called a shift matrix, and this is my clock matrix, where zeta is a phase factor. It's e to the 2 pi I over q. So I have a matrix that's a bunch of phases, and I have the cyclic permutation matrix, basically. And those 2 matrices will not commute, but they commute up to a phase, which I call e to the I h bar, where h bar is 2 pi over big Q. Now, it turns out that any matrix can actually end by a Q by Q matrix can be expanded in terms of powers of this U and V. In the large Q limit, U and V almost commute. So I can think about space of matrices actually as a space of almost commuting functions of variables little u and little v, where little u and little v are defined like so. However, big U and big V don't commute, and therefore these matrices will live on a non-commutative space. And it turns out that the matrix multiplication in this way of parameterizing the matrices defines what's called a star product, where the normal multiplication of matrices indeed becomes a multiplication of functions with a star product, which means that you're multiplying the functions, but you do this thing that's basically a Moyal product. It's e to the I h bar du dv tilde minus du tilde dv of the product. And then after taking the product, one has to take u and v to be equal to u and u tilde to be equal and v to be v tilde. So it turns out that the space of matrices can be viewed as a function space on what's called then a non-commutative torus. So U and V are defined modulo 2 pi, and the matrix multiplication becomes then this star product multiplication. But in the large Q limit, somewhat mysteriously, this thing becomes commutative. And if you think about it a little bit more deeply, it only becomes commutative if the functions that I'm multiplying are sufficiently smooth. So indeed, if I would be allowed to restrict to smooth enough functions, then the star product becomes the ordinary product. And this is actually where the kinetic term will become important, because the kinetic term that I'm going to be introducing should allow me to restrict to at least functions that are sufficiently smooth. And this is indeed going to be happening if the kinetic term will effectively act like a time derivative. So by the way, this little u and little v indeed will then play the role of this bilocal time of the SYK model. Let me speed up a little bit, although the next step is still kind of technical.
Herman, can I make a short comment?
Yeah, sure. Good.
It is quite established that this two-matrix model is basically equivalent, mathematically equivalent to integer quantum Hall effect, but in some non-homogeneous magnetic field,
right,
determined by these potentials, by those potentials. And it's important that it's integral quantum Hall effect, so it's basically free fermions in magnetic field. But magnetic field is determined by the potentials. Just a comment. That's why.
That's an
representation.
I would like to learn more about it, because actually later on it turns out that this matrix model indeed exhibits something. I talked about this color flavor map. And it turns out that because the quantum Hall, from the point of view of string theory, can be viewed as putting D0 branes on a bunch of D2 branes. It's like magnetic flux on engagement. And it turns out that, anyway, I'd like to understand better your comment, because it turns out that there's basically also a T duality in the story here. It turns out that this color flavor map can kind of be
yes, certainly. And this one matrix and another matrix somehow represent two directions in a plane where electrons live.
Yeah. Okay. I'd like to learn more about it.
That's why this Heisenberg group, representation of Heisenberg group with U and V appears, as you mentioned, and also and also area preserving diffeomorphisms.
Right. So indeed, the large Q limit obviously will then be the large B field limit, so that the lambda level sort of starts shrinking to points. And indeed, the fermions indeed are just functions of one of the variables. So since the fermions are vectors, they're bifundamentals, if you wish. So I'm going to write them as functions of V. They all have an I index still. But in terms of the Q indices, I'll replace that by V. So V is a basis such that the big V matrix will multiply times e to the I little v, and the big U matrix will just shift V by an amount H bar. Turns out that the trace indeed will just be integrating over the plane, the UV plane, and the inner product in this case is just integrating over a single V variable. Now at this point, indeed, I'm going to choose my matrix X Q to be this in terms of the U matrix. And the motivation at this level, at least, is that this is the operator that if I let it act on psi, when I view psi as a function of V, it will shift it either up by H bar over 2 or down by H bar over 2. So this is indeed what you would call a discrete derivative with respect to V. So in the matrix language, this is as close as you can get to a derivative. And therefore, in that language, this kinetic operator will now indeed look like the kinetic operator of an SYK model.
But so here you kind of chose it to be something nice. It could have been a completely non-local in time.
Right, it could have been a non-local in time. I'll make a comment later that this choice actually happens to have a pretty natural interpretation in terms of the matrix model.
Okay. Because the IR physics would be very different, I guess, if there's something.
Right, and let me make one other comment. Suppose that I would do the following, that I would allow myself to say, hey, I take XQ to be this thing plus something else, okay?
Mm-hmm.
Then I can still take this thing to be my leading order kind of action, and I can call this something else higher order couplings.
But it might be relevant.
It might be relevant, precisely. So then indeed you have to do an RG analysis, whether or not the higher order couplings might be relevant or not. Mm-hmm. So that's the correct question to ask. Okay. But yeah, correct. No, that's a fair point. So anyway, so I'm ending up indeed now indeed with a thing that looks even much closer to the SYK model. It's rewritten now in this particular form with this star product. Indeed, I have this discretized time derivative. I'm now also introducing the sigma field, and now this thing looks indeed like the SYK model, but on this non-commutative torus. One difference with SYK is that the psi's are complex, so it's a psi dagger psi thing, and that turns out to have a pretty interesting sort of byproduct. So let me now at this point imagine that I could indeed take the large Q limit and indeed be left with a continuum theory, and then I can do the usual thing. Suppose indeed that I'm just focusing on the kinetic term. I could then say, hey, the psi's become Majorana oscillators after quantization. The fact that it's complex actually means that this object GUV satisfies a reality condition that the star of GUV is the G at VU. So there's a non-local reality condition at that point. But anyway, so this is basically the punchline of the proposal, and the question is this going to help us understand more how to think about the SYK model? Why does it produce two-dimensional gravity? Are we learning something about non-critical string theory? What's the target space interpretation of non-critical string theory in the presence of a large number of FZZT branes? These are the questions that hopefully one can start studying, and that should put this proposal on some solid footing. So unless there are questions, I'll end with a number of comments. So one comment is indeed this matrix X sub Q. So let me just explain that in terms of this picture. So there's this picture here. This picture is actually the spectral curve. It turns out that if you take the two matrix model, indeed, as we were discussing with Emil, so there are two possible operators you can write down: the determinant of X minus B and the determinant of Y minus A. X and Y are two variables that parameterize the eigenvalues of the matrices, and they satisfy a relationship that specifies a two-dimensional curve. Turns out that curve has higher genus, and it actually has for a P comma Q minimum model. So this is, I should say, suppose you start with the P comma little q minimum model. So for quite a while, or minimal string, say. For quite a while, I was actually very tempted to identify big Q with little q. And the reason why I was tempted to identify big Q with little q, it turns out that if you take the P comma little q minimal string, and you write down the spectral curve of the P comma little q little string, minimal string, that this matrix X sub Q, in the case that big Q is little q, has eigenvalues that precisely sit at what's called the pinched points, the pinched singularities of the P comma Q minimal curve. So basically our FZZT branes are sitting at these locations over here. So anyway, so that's a natural set of locations from the point of view of P comma Q minimal string theory. However, it turns out that you cannot literally say that the P comma little q minimal string will automatically put FZZT branes at those locations, but still it's a natural set of locations. It also turns out, and this comes back indeed to the question that was also asked earlier, that in order to connect with minimal string theory, I actually have to do something different than in order to connect with SYK. So if I start with n FZZ branes, and I would introduce, say, a couple of FZZT branes as a way of introducing the potential for the B matrix. Then in order to take the double scaling limit that will give me the minimal string, I have to take n to infinity first. And the double scaling limit for the minimal string theory sits in this corner up here where n goes to infinity first. In order to get this continuum as SYK model, I have to do the opposite. I basically have to take Q to infinity first. And I'll explain a little bit more later why. But you have to take Q to infinity first. And therefore, you're basically going to sit at another part of the phase diagram. Basically, you have to take Q to infinity, and the SYK model sits here. And there's a rather natural separation between the two regimes, where actually big N, the number of FZZ, sorry, the number of ZZ branes is little p times big Q, because basically it turns out that for every FZZT brane, you basically absorb a little p ZZ branes. So there's a rather natural dividing line. But this is our proposed phase diagram that if you look in the parameter space of minimal strings with arbitrary number of ZZ and FZZT branes, that the SYK model sits here and the minimal string sits there. Yeah, a few further comments. Let me be very quick here. One of the motivations for us initially to think about connections between between the SYK model and minimal strings came actually from the double scaled theory. So the double scaled SYK model, you can rewrite this G sigma theory with the G and the sigma variables in the limit where n goes to infinity, but the order of the interaction p squared over n. So p goes to infinity too, but in a way where p squared over n is fixed. That's called the double scaling limit. And it turns out that the bilocal field theory of the SYK model takes the form of a Liouville theory. You get an ordinary kinetic term, and you get this interaction, this g to the p interaction becomes an exponential interaction. But this Liouville theory turns out to have a complex central charge. And it turns out that the central charge of that Liouville theory is 13 plus I times a number that depends on p and n. Actually, this is a typo. This should be pi. But it turns out that in our case, we actually have, because of the fact that we had this complex fermions, it turns out that we have two Liouville theories, and with a complex conjugate central charge. So our continuum theory actually can be rewritten as a Liouville theory that has, where each Liouville theory has central charge 13 plus an imaginary number, the other one 13 minus an imaginary number, and the total central charge adds up to 26. So there's another indication actually that SYK has something to do with something that you might want to call a generalized minimal string theory, and this is the other motivation of looking for that particular connection. Last, since I'm sort of ran out of time, last two comments. In the end, we want to find sort of some kind of target space interpretation. Can we understand now better why the target space of SYK is a black hole? Perhaps we can connect it indeed with earlier models of low-dimensional black holes or string duals of low-dimensional black holes. There's a brief comment about a T-duality where basically the flavor color transformation that I indicated can actually be viewed as a T-duality. But in order to, let me end with one final comment. So again, part of the motivation of this project, or at least this proposal, is to try to embed SYK as a potential holographic dual of a target space gravity or string theory, but through a mechanism that's much closer to the usual open-closed string duality that we're used to in string theory. In the way ADS-CFT was derived was indeed as the large n limit of open strings on a set of D branes. One of the slight confusion, at least conversations that's going on right now is that up to now, when you take a large n limit and you have a duality between a large n theory and string theory, n labels the number of D branes. In the recent literature, people have been looking at matrix model duals of JT gravity, where indeed the target space gravity theory is then modeled as a matrix model. But surprisingly, in that case, the matrices are not the open strings, but the matrices are actually the random Hamiltonian. So the Hamiltonian becomes the matrix in the recent discussions. And in that case, the rank of the matrix, which is then the size of the Hilbert space of the Hamiltonian on which the Hamiltonian acts. So the rank of the matrix is the dimension of the Hilbert space. So it's e to the power the entropy. And e to the power the entropy is much bigger than the number of D branes. So let me just make one comment about this. So for a while, I thought that what we had was very different than what, for example, what Schenker, Stanford, and Saad are doing. But actually, it turns out that the two things are much more closely related than I initially thought. And the argument is the following, is that it's true that in our initial matrix model, we started with n by n matrices, which led to n fermions. So we had n size. So n is the number of SYK fermions, which leads to a Hilbert space which is 2 to the n dimensional. But in our story, we also introduced Q. And Q is the number of FZZT branes. And in the end, we introduced this matrix X sub Q, which had to become DDT. Now, in order to take a continuum limit of a theory with a very dense random spectrum, you need DDT to be very accurately represented by that matrix X sub Q. And it becomes clear that the matrix X sub Q should be thought of as a matrix that has at least e to the power the entropy many entries. So in order to really take the continuum limit of our theory, our Q would indeed have to grow like e to the S. So in that respect, it's probably true that our large n limit or our continuum limit in the end could still produce a similar kind of 1 over n expansion, or in our case then a 1 over q expansion that would then match with the things that people are currently looking at in the connection with wormhole spacetimes in JT gravity. Since I took up already a few more minutes than an hour, let me stop here. Thank you.
Thank you very much, Herman. We have time for a quick question if anybody has one before, if we take a break. So if anyone has a question, please go ahead.
So on this last comment, so then you're expecting the sorts of things that people worry about in 2D black holes having to do with chaos and spectral statistics have to do with this last comment?
Right. So by the way, I think that this last comment, let me make one other comment about this too. So when people talk indeed about the averaging that's needed in order to understand these wormhole contributions, in my mind, actually time plays a pretty important role in this discussion. So especially, for example, if you talk about the spectral form factor, the spectral form factor has a smooth behavior in the ramp and the plateau only after you're doing the averaging. But one way of doing the averaging would be to do time averaging. And it's true that one of the reasons for why you actually get any features at all in a spectral form factor is because you have different systems where you assume that you know how to synchronize clocks on both systems. So if you no longer know how to synchronize clocks, you have to start doing time averaging. So I think time plays an important role in recent discussions. And sort of the same thing is happening here as well, where indeed the extent to which you can actually identify individual energy eigenstates depends on how much control you have over time and over how long you can actually do a measurement. So that I think I think relates to the recent discussions. One other comment, of course, is, and there was a question about this, is that we're making in this construction contact with the disorder averaged SYK model, which is kind of confusing because you might have thought that string theory is the most fundamental perspective on these kind of systems. So why wouldn't string theory actually know of the actual individual SYK model if the SYK model has only one choice of random coupling? So you might think of the individual SYK model in the ensemble as being the fundamental theory, and then the ensemble average description is the one that would correspond to the minimal string, or at least is related to string theory. So there's actually a bit of a debate whether or not, in this case, one has to do averaging in order to even make contact with string theory. And that is not just a matter of making contact with gravity, but even making contact with string theory.
But even before I do any kind of ensemble averaging, so even if I just take a single instance of a random Hamiltonian, it's going to have random matrix statistics. And it sounds like from your last comment, those random matrix statistics are going to have to do with something other than the random matrices that you're integrating over, because that has to do with this matrices that are of size e to the s rather than the matrices that are size s. In other words, the random matrix statistics that people talk about in the context of SYK and JT gravity has to do with the random matrix statistics of the matrices of size e to the s.
Correct, but I was arguing that Q would have to be of size e to the s if I want to be able to view the non-commutative SYK model as a good approximation of the continuum limit.
Right.
So in order to completely capture the random matrix statistics of the continuum SYK model, Q would have to be of order e to the s. So what's sort of interesting perhaps is that this actually allows a way of viewing Q indeed as the thing that whose 1 over Q expansion sort of reproduces these higher order topologies.
Okay.
But it's just an intuitive comment. I don't have a practical way of implementing this.
Okay. Let's thank Herman again. I'll stop the recording here.